What does the term NVIS mean as related to antennas? It stands for Near Vertical Incident Skywave. You'll remember that we talked about this in the first session, where the wave is shot nearly vertically into the sky and then comes back down from the ionosphere for coverage of nearby stations. So we send our signal nearly straight up because we want to communicate with stations that are nearby, possibly located in valleys in the mountains, and this sort of thing that we could not do with VHF. If amateur practice is usually to send signals out at a low angle of radiation because we go for maximum range. We want to go out here and reflect off the ionosphere to get us a long-range signal. But in this case, we want to communicate with nearby stations, so we send our signal straight up in order to communicate in this manner. Here's an example of a portable NVIS antenna that I built. This is for 40 meters, and I think I showed you this before also. It's only about 5 feet above the ground. This is the antenna wire here. This is a dipole. It's fed in the center right here. The other end on the other side of the center is just like this. Insulator here, insulator at the far end, center feed, and then down underneath here I have a reflector because the soil here on the Big Island is really bad as a electrical conductor, and so I laid a reflector wire down here just like the reflector on the Yagi. This helps to reflect the signal straight up, which gives me good skywave coverage on the nearby islands here. And using this antenna, I can communicate up and down the island chain on 40 meters because I get the near vertical incidence skywave that lets me do that. This is a really handy antenna. Sets up in about 10 minutes, and it's not one that I leave up. My wife owns the backyard. I only own the sky above it, so I only put this up occasionally. But a very handy antenna for emergency operation. I can take it out, set it up in just a few minutes, and have HF communications up and down the island chain. Which of the following is an advantage of an NVIS antenna? High vertical angle radiation for working stations within a radius of a few hundred kilometers. What height above ground is an NVIS antenna typically installed? Between 1/10 and 1/4 of a wavelength, and often even less. The one I just showed you is even less than that, but they're installed close to the ground. What's the primary purpose of antenna traps? Let's see what we're talking about with antenna traps. Here's a diagram of a trapped antenna, and it looks like a dipole except it has these things stuck in here. And what these things are is combinations of capacitors and inductors that are tuned to a particular frequency. This happens to be a 3-band trapped antenna. Okay? So what's happening here is we're feeding a signal into here in the center of the antenna, and then let's say it's a 10-meter signal. Okay? If it's a 10-meter signal, 28 megahertz signal, that signal can only get out this far on the antenna. So when I have a 10-meter signal, the transmitter sees only this much of the antenna, my 10-meter portion of the antenna. Okay? If I have a 15-meter signal, a 21 megahertz signal, that can blow right through the 10-meter trap and get all the way out here to the 15-meter trap where it's blocked. Okay, so now for 15 meters, I have the longer antenna that I need for the longer wavelength, from here to here. And then for 20 meters, I blow right through this trap also, all the way out to the insulator, and now I have a 20-meter antenna that stretches all the way from here to here. It's all one hanging up piece of wire with a few traps in it, a single feed line, and it permits multi-band operation using the trapped antenna. What's the advantage of vertical stacking of horizontally polarized Yagi antennas? It narrows the main lobe in elevation. It will take the main lobe of the antenna, and instead of making a high lobe, it makes a narrower lobe in elevation. It concentrates more of the signal in the direction that you want it to go instead of shooting more of it typically up. But it narrows the main lobe in elevation when you vertically stack horizontally polarized Yagis. Which of the following is an advantage of a log periodic antenna? Let's take a look at what a log periodic antenna is. Here's a really good view of a log periodic antenna. Looks kind of like a Yagi, but it's not. And the advantage of it is a wide bandwidth, and in fact an extremely wide bandwidth, with continuous operation through the whole bandwidth. Here you can see a really tiny one for very high frequency, or actually ultra high frequency, and you can see that it has these elements on the two sides here, and you can see through the board material there that there's an etched element on the far side of the board there. You can just barely see through there. So you have an element here that's on this side, on this side. Here you have an element that's this side and this side. Here you have an element that's this side, and so on. Now, but the trick of a log periodic antenna is that they have a wide bandwidth. These are not a real common antenna for hams. I do have a friend who is a ham who has a log periodic antenna. It's still in a box of 1,000 pieces, and he may get it up someday, but it's not real high on his list. They're very complicated antenna, and with a quite an investment in time as well as money to put them up. They're mainly used on government and military stations where the wide bandwidth is a big advantage because it gives them a broad range of frequencies they can cover. Which of the following describes a log periodic antenna? The length and spacing of the antenna's elements increases logarithmically from one end of the boom to the other. Now on the log periodic antenna, the antenna is fed at the smallest end of the antenna right here. Okay, and unlike the Yagi, all of the elements are driven elements. There are no parasitic elements. And if you look here, you will see that the feeding of this, I feed it here, and then before it gets to the next element, the feeding switches sides. So that I'm feeding this element out of phase with this element. And then it switches again for this element. So I'm feeding this element out of phase with this element, and so on, all the way up the antenna. And the spacing and the length increases logarithmically from one end of the antenna to the other. The direction of the beam is toward the short end of the antenna. The feeding end of the feed point of the antenna is on the short end of the antenna, and all of the elements are driven. Why is a beverage antenna not used for transmitting? It has high losses compared to other types of antennas. A beverage antenna has high losses compared to other types of antennas. Which of the following is an application for a beverage antenna? They're used for directional receiving for the low HF bands. Now, one reason they're popular for this, even though they have high losses, is that they're quite noise-free. They receive well on the low-high frequency bands without picking up a lot of noise. So people who are looking for a low-noise receive antenna use the beverage for receiving only, and then they use a different antenna for transmitting. And that requires either a transceiver that's adapted to do that, or a separate transmitter and receiver, or some other arrangement. The ordinary, especially the lower cost transceivers, won't do that without some kind of a switching arrangement. Which of the following describes a beverage antenna? It is not a vertical antenna constructed from beverage cans. So you can throw that trick question out. It's a very long and low directional receiving antenna. And what it is, it's a wire antenna, fairly low, typically 5 feet above the ground, and typically about 1,000 feet long. And it's matched by a 4-to-1 RF matching transformer here. It has a terminating resistance at the far end. It is directional in this direction. So it's directional from the direction that has the grounded resistor. All right? So it's going to hear best from this direction, and it's best for receiving. It's a very long and low directional receiving antenna. Which of the following is a disadvantage of multi-band antennas? You remember we looked at that trapped antenna, the multi-band antenna? And you remember that at one point we talked about bands being harmonically related to each other, that the 10-meter band is harmonically related to the 40-meter band and so on. Multi-band antennas have poor harmonic rejection. So if you have a transmitter that's producing harmonics, the multi-band antenna will go right ahead and transmit those harmonics.